Good morning, everybody, and happy Monday. We're going to be starting a brand new section today in your science books. This is our last section in Chapter 11 dealing with forces in fluids. So we're going to be looking at Section 4 in your books, which is talking about Bernoulli's principle. Now, you can find this section starting on page 437. And as always, we're going to start out with a very simple science demonstration, which is going to demonstrate Bernoulli's principle. Now, all you need in order to do this little demonstration is a simple piece of paper. Now, don't worry, I'm not going to ask you to videotape yourself doing this, but you can try this at home. You can find any old piece of paper. It could be printer paper or notebook paper. All you're going to do is you're going to take the piece of paper and you're going to hold it between your index finger and your thumb. You kind of want to curve it over so that it's like facing towards your face, like the top edge is looking, flat. Now, obviously, if I were to blow some air underneath at the paper hanging down, we can very easily guess what's going to happen. All right. Obviously, when I exhale, I'm forcing air, and that's pushing my piece of paper up. Now, the question I have for you is, instead of blowing below the paper, what if I were to blow a stream of air up above the top of the paper? All right, we're going to try this out. So ready? And I'm just going to take my lips, going to put them at the top of the paper, and I'm going to blow over the top of the paper, not below it. And all right. Now, believe it or not, what you guys just witnessed, the principle at work that's explaining how that piece of paper is able to lift up, even though I'm blowing air over the top of it, explains to us how it is like large airplanes are going to get up off the ground. So Bernoulli's principle, even though when Bernoulli was first doing his work, he was doing experiments with like liquids like water, but the principle that is at work here is actually going to explain to us how airplanes fly. So very quickly, I want to go over a brief history of flight. Now, on page 437 in your books, it talks about the Wright brothers and the first manned flight in a fixed-wing aircraft. And the fact of the matter is that people have been flying around in other kinds of airships for a couple of centuries. And that would be an example of, instead of flight with airplanes, this would be flight with, say, like a hot air balloon. Which the first manned hot air balloon flights were happening in the 1700s. Now, this works on a principle very similar to what we learned about in the last section when talking about like Archimedes' principle and buoyancy and density. And basically, the way a hot air balloon is going to work is you create a region of low density inside a balloon by heating up the air inside, hence hot air balloon. Okay, so if you have low density inside the balloon, and you're going to have high density or higher or more dense air outside, you're creating lift because of a difference in density. So that lower density inside the balloon is going to push it up. Really, what's going on here is you have a buoyant force created by the atmosphere. And that's what's going to cause the balloon to lift up or float up in the air. All right. But when we're talking about things like airplanes or jets, they're going to rely on a completely different principle. We're not talking about Archimedes' principle of buoyancy, but rather this is Bernoulli's principle of lift. Now, earlier you guys saw as we were, just taking this regular old piece of paper here and blowing over the top of it, you could see that the piece of paper was lifting up. So we're going to talk about what's happening there. All right. If you guys flip over onto the next page, on 438, you can see a paragraph about Bernoulli's principle. And basically, Bernoulli's principle states that faster moving fluids are going to have a lower pressure than slower moving fluids. So we're not talking about high density versus low density, okay? But this is, according to Bernoulli's principle, fast moving fluids have low pressure, while slow-moving fluids have higher pressure. Okay, so basically what was happening, when I was blowing that stream of air over across the top of the piece of paper, that stream of air was creating an area of low pressure. Okay, so fast air was giving me low pressure, which means beneath the paper, I had an area of high pressure. Now I want you to think way back to 7th grade. If you had me for 7th grade, one of the things we talked about was something called osmosis or diffusion. And in osmosis and diffusion, substances are always wanting to go from an area of high pressure or high density to low. And that's what's happening here with this piece of paper. We've got high pressure here, low pressure here. That high pressure air wants to get to that area of low pressure, and so it creates an upward force. It creates lift, all right? So that faster air creates low pressure. The high pressure wants to get to the low pressure. It always wants to go from high to low. That's how things work in nature, okay? Now, the way that this idea is applied to, say, like airplanes today, is going to be related to how an airplane wing is shaped, all right? Now, if you look over on page 439, you can see it gives you the shape of a cross-section of an airplane wing, which is going to look something like this. Okay, and that shape, and I'm going to fix it right here, because I know some of you guys are really bothered by the fact that that little line didn't connect. All right, that shape is called an airfoil. Okay, now airfoils are shaped the way they are because as that plane is moving forward, so its engines are causing a forward motion, air is passing above the wing and below the wing. Right? Now this shape is going to cause air to move faster over the wing than the air moving under the wing. Okay, so I'm going to have fast air on top, slow air on the bottom. Now, if that's true, that means I'm also going to have an area of low pressure above the wing, and that slower air is going to have high pressure below the wing. If I can create an area of high pressure and low pressure, that's going to create an unbalanced force. And the high is always going to want to go to low. And this is going to create an upward force. We call that lift. All right? So this is what's allowing airplanes to fly. The shape of their wings is going to create a difference in fluid speed. The faster the air, the lower the pressure. And that is going to create an upward force. Now, there's another application to this same exact principle. If you were to take a look at the shape of car spoilers, in other words, so those little wings that go on the back of cars, they actually serve a purpose. So they're not just there to make the car look cool, they're actually performing a function. And basically, if you were to look at the shape of a spoiler, it's basically an upside down wing. It's an airfoil that's been turned upside down. Now, what's the purpose of that? Well, let's think about this. All right, so let's say I take that same airfoil shape and now I turn it upside down. All right, which means that as the car is driving forward, air is going to pass underneath the wing, and that air going under the wing is going to be fast. Okay, which means it's going to have a low pressure. Air going over the wing is going to be slower, which means it's going to have a high pressure. So let's think about this. If I have high, slow moving air or high pressure air above the spoiler, and fast-moving, low-pressure air below the spoiler, which way is the force going to go? Well, let's think about this. If the airfoil, when it's right side up, creates lift or an upward force, if I turn that wing upside down, the difference in pressure now is going to push down on the spoiler. Okay, so remember we're talking about car spoilers here. So instead of an upward force, I get a downward force pushing down on the back of the car. Well, what's the point of that? Well, basically, with cars at least, the higher your speed or the faster you're going, the more traction or connection you want with the road. And so if you have a spoiler on the back of your car pushing down on the wheels, it's going to create a greater amount of friction or connection with the road, and you're less likely to lose control and spin out. All right. So this is kind of, Bernoulli's principle applied. Instead of causing lift, it's causing a downward force. All right. Which, if you were to think about this, if an airplane had been built improperly and its wings had been installed upside down, when that airplane tries to take off, instead of lift, it's going to create a downward force, and there is no way that airplane could fly. It's got engines, it's got wings, but those wings are upside down. It's creating a downward force instead of an upward force. All right? And it all has to do with this difference in airspeed. So remember, with Bernoulli's principle, fast-moving fluids always have low pressure. Slower-moving fluids are going to have higher pressure. All right, so in your books on page 438, you can see another little demonstration of Bernoulli's principle, at least as it's working in air. Okay, so remember that air, because it's a gas or made of a mixture of gases, it's a fluid. And so it's going to behave according to these same principles that we're talking about. So Bernoulli's principle works for both liquids and gases. All right. So what I have here, I've just got two aluminum cans, and you don't have to try this at home. And I have them suspended on strings. Now what I'm going to do is I'm just going to blow a stream of air in between the cans. Now what do you think is going to happen? Is that stream of air going to force the cans apart, or is it going to make them push together? All right. Well, let's think about this. So according to Bernoulli's principle, fast air has what kind of pressure? Fast air has low pressure, which means the slower surrounding air is going to have high pressure. So let's look what happens when I create an area of faster moving fluid in between the cans. Watch. All right, so we can see that they touched together, or they were rather forced together. Why? Well, as I passed that air in between the cans, it created an area of low pressure. That low pressure, right, means that on the other side of the cans you have high pressure. And that high pressure is going to push in against the cans, causing them to touch. Let's do it again. Okay, so there's Bernoulli's principle. Okay guys, so this last demonstration I'm going to be doing is actually going to be part of an extra credit assignment that I'm going to make available to you guys. And if you are able to correctly explain to me what's going on when I do this demonstration, it's going to be worth an extra 20 points to the quiz that you guys just took. So here's the demonstration. So as you can see, I've got a hair dryer forcing air up, and it's holding this little ping pong ball in place. Now, it would make sense that when I force air, it's going to push against the ball and force it upward against gravity. But what would happen if I turned my hair dryer and did that? In fact, I can go and I can do it the other way as well. Now, you might expect the air to force the ball and just shoot it off to the side, but instead, when I turn the hair dryer, it floats in midair. Now, if you can write to me in a paragraph an explanation for why it is the ball is able to float in midair the way it does, that will be worth an extra 20 points on the recent quiz that you guys just took from me. So you can go ahead and find that assignment on Plus Portals. I'm going to look forward to your replies. It's going to be due by Friday.